Invisible flickering on the Sun could predict potentially dangerous solar flares hours in advance. Images captured by the Solar Dynamics Observatory have revealed the coronal loops giving off sub-flashes of ultraviolet light before the solar flare, which could act as an early warning system for dangerous space weather. Shining loops of plasma on the surface of the Sun flicker hours before they unleash potentially dangerous solar flares. The new findings could help create reliable space weather forecasts. Solar flares are violent outbursts of electromagnetic radiation that shoot from the Sun when invisible magnetic lines at the Sun's surface get twisted up until they eventually snap. These outbursts most commonly occur around sunspots, dark patches where magnetic fields line up, poke through the home star surface, and then pull up the plasma from the Sun's surface into shimmering horseshoe shapes, known as the coronal loops, before they blow their tops. These stellar explosions can send waves of radiation towards the Earth, trigger temporary radio blackouts. The flares can also unleash fast-moving clouds, magnetized plasma, known as coronal mass injections, and can occasionally slam into the planet and cause geomagnetic storms, such as in May 2024, when they experienced the most powerful geomagnetic storm in 21 years, which painted widespread auroras across the globe. In the new study, January 5, 2025, in the Astrophysical Journal Letters, presented also January 15th, the American Astronomical Society in Maryland, researchers analyzed multi-wavelength images of coronal loops preceding 50 solar flares filmed by the establishment Solar Flare Dynamics Observatory. This revealed that the loops emitting small flashes in visible ultraviolet light at a specific wavelength shortly after the flares were unleashed. The researchers noted that this flickering could signal oncoming flares 2 to 6 hours ahead of time with 60 to 80% accuracy, which is a significant improvement over the current methods. The intensity of the flickering also relates with the power of the incoming flares. Currently, the Sun is spitting out solar flares like there is no tomorrow, thanks to the ongoing solar maximum, the peak of the Sun, roughly 11-year cycle of activity. So indeed, there will be no shortage of data for the follow-up studies. Forecasting solar activity is extremely challenging, and scientists can still get predictions wrong. For example, an ongoing solar minimum arrived early and has been more active than scientists initially expected. The uncertainty that can cause issues when surprise solar storms can catch us out. For example, satellite operators lost multiple spacecraft in recent months after they were knocked out of low Earth orbit by unseen fluctuations in the Earth's atmosphere caused by the storms. On the Earth's surface, the GPS systems, such as those used most tractors across the US, also experienced malfunctions during the biggest geomagnetic storm disturbances last year. Electrical currents generate these storms can also damage ground-based infrastructure, such as rail lines and power grids. Being able to be more accurately predict space weather would also give the Aurora Chase a better chance of seeing the northern lights. But most of the current methods forecasting space weather, such as measuring geomagnetic strength and analyzing sunspots, do not give accurate estimates for when the specific flares will occur. However, the new method of predicting solar flares can provide more advanced warning by taking into account the individuality of each potential solar outburst. Electric propulsion are being increasingly used on space missions and could ultimately replace thrusters using chemical rockets. So folks, spacecraft powered by electric propulsion could soon better protect against their exhaust thanks to new supercomputer simulations. The electric propulsion is a more efficient alternative to traditional chemical rockets and is being increasingly used on space missions, starting off with prototypes with the Space Agency's Deep Space One and the European Space Agency Smart One in 1998 and 2003 respectively, and also subsequently finding use on flagship science missions such as the Dawn missions, and the asteroid belt. Continuing, there's even plans to use the electric propulsion on the agency's Lunar Getaway space station. The idea behind the electric propulsion is that an electric current ionizes, removes the electron from the atoms of natural gas such as xenon and krypton studied on board the spacecraft. The ionization process produces a cloud of ions, electrons. Then the principle, called the Hall effect, generates an electric field, accelerates the ions and electrons, and channels them into the characteristically blue plume that emerges from the spacecraft, well over 37,000 miles an hour, that is 60,000 kilometers. According to Sir Isaac Newton, the third law of motion, every action has an equal of opposite reaction. The plume of ions jetting out to the spacecraft therefore acts to provide the thrust. It takes a while for the build-up of thrust. However, because despite moving of the high velocity, the ion plume is pretty sparse, the pulse generated is not as immediate force as a chemical rocket, but the ion engine requires less fuel and therefore less mass. This energy of the electromagnetic fields is often provided as solar arrays, and hence the technology is sometimes referred to as solar electric propulsion. But the missions farther from the Sun, where the sunlight is fainter, nuclear power in the form of thermoelectric generators could also be used to drive the electric propulsion. Through electric propulsion is now maturing and is being used in a variety of missions. It is not perfect technology. One problem in particular is that the ion plume can damage the spacecraft. Though plumes is pointing away from the probe, electrons of plume can find themselves redirected, moving against the plume's direction of space. Impact of spacecrafts, damaging solar arrays, communication antennas, and any other part exposed to the components. So folks, indeed, for missions that could last for years, electric propulsion thrusters must operate smoothly, consistently, over a long period of time. Before solutions can be put in place to protect the spacecraft from these backscattered electrons, their behavior of the ion engine plume must first be understood. They performed supercomputer simulations of the ion engine exhaust, modeling the thermodynamic behavior of the electrons and how they affect the overall characteristics of the plume. These particles may be small, but the movement of the energy played by the important role determine the dynamics of the plume emitted from the electric propulsion thruster. They explain as well that the electrons, the plume behave differently depending upon their temperature and also their velocity. These electrons are a lot like marbles packed into a tube. Inside the beam, the electrons are hot and move fast. The temperature doesn't change much, and if you look along the beam direction, however, if the marbles roll out of the middle of the tube, they start to cool down. The cooling happens more certain in a direction, the direction in particular to the beam's direction. In other words, the electrons in the core of the beam are moving a lot faster, having more or less constant temperature, but those on the outside cool off faster, slow down and move out the beam, potentially being backscattered, impacting a spacecraft. Now that scientists better understand the behavior of electrons and ion plume, they can incorporate of these designs for the future electric propulsion engines, looking for the ways to limit the backscatter, or perhaps confine the electrons more to the core of the beam. Ultimately, this could help missions powered by electric propulsions to fly further into longer distances, pushing the gentle blue breeze of its ion plume.